So what actually is an electric field? Well, it is the electric force per positive unit charge at a certain point. So now, instead of having two charges and looking at the interaction, which we did when we were looking at the force of one on the other, now we just have one charge. Now we can't calculate the force because there's nothing for it to have a force on. However, it would still be useful to know what the force would be on a second charge if we put one there. And that's what the electric field tells you. The reason we say the force per unit charge at a point is that you need to pick somewhere and say the electric field at that point is such and such. You can't just say the electric field due to this charge is such and such, as it will change depending on which point you choose. So obviously if you are closer to the charge, the electric field will be stronger and the force, if you were to put another charge there, would be stronger. So here is the equation for electric field. So the electric field is the force a second charge would feel exerted by Q1 if we place a second charge there. I'm sure you've all heard of electric fields before, but a field is actually quite a strange concept. We're saying the amount of force a positive charge would feel if it were there, even though there's nothing there now. Or another way of saying it is that you could say Q2 is a 1 coulomb charge, and the electric field is the force on that unit charge at that point. So if there is no second charge, then what direction is the unit vector in the equation pointing? Well, r is the distance to the point we are measuring at. So remember, we had to specify a measurement point, which is the point we would put our second charge at. And r hat there, the unit vector, is in that direction. So all we have to do to get back to the force is multiply the electric field by the second charge. The units of electric field can be found by just rearranging that simple equation to be newtons per coulomb, which makes sense, as we've said the electric field is the force per charge. Now moving on to field lines, which are a way of representing a field. There are a few rules about how to draw them. The first rule is that the field always points in the direction a positive test charge would go if you put it there. So the field lines around a positive charge would look like this, all pointing outwards, because if we put a positive test charge near to that positive charge, it will be pushed away. And the electric field lines around a negative charge would look like this, because a positive test charge would be pulled towards the negative charge. Now, these two charges are separated at the moment. What about if we put them together? What would the field lines look like? Try pausing the video and drawing them out, just from what you know about the first rule of field lines. So the field lines around this pair of charges would look like this. So all the field lines begin on a positive charge and end on a negative charge. And that is the case with all systems with net charge of 0. So when all of the charges add up to a total of 0. And the last rule you need to know about field lines is about the density of the field lines. If we draw the field lines more densely packed together, then the field is stronger. A more official way to say this is that the number of field lines per unit area through a surface perpendicular to the field lines is proportional to the magnitude of the field in that region. So looking at the diagram, what does that mean about the field closer into the charge? Well, closer in, the field lines are actually more densely packed than when you move further away, so that tells us that the electric field is stronger closer to the charge, which we know is true because the equation for electric field has a 1 over r squared in it.